The subject of my talk is nodal sets of eigenfunctions of the Laplacian on a basically compact Riemannian manifold. So there are two parts to my talk. The title was Local and Global Analysis of Nodal Sets. And there are two parts to my talk. One is about the recent proof by Alexander Logunov and Eugenia Malinnikova of Yau's conjecture on hypersurface volumes of nodal sets of eigenfunctions. So I decided to talk about the upper bound. Logunov has both an upper bound and a lower bound. I decided to talk about the upper bound because it's easier to talk about. It's easier to explain it. And Alexander Logunov's proof is a triumph of the use of local techniques. On the other hand, I want to mention some recent results by Junhyuk Jung and myself on counting nodal domains of eigenfunctions on surfaces. So this is a kind of, this is a good example of what's called a global problem. There's no way that you can understand nodal domains and count them by only studying small portions of the surface. And also the techniques are the techniques of microlocal analysis or semi-classical analysis. So the techniques are also what we think of as being global analysis. So, okay. So let me just write down notation. This is a talk in classical analysis. There are very few definitions. And the notation is probably familiar to everybody here already, although I have some unusual conventions. So I'll be on a really mostly compact Riemannian manifold of dimension little m. And there's a local formula for the Laplace operator on any Riemannian manifold. The notation is familiar probably to everybody. The G lower ij is the metric tensor, G upper ij is its inverse, G is a determinant. And if you're on a compact Riemannian manifold, then there exists an orthonormal basis of eigenfunctions. So orthonormal means that these inner products are delta ij. And the only unusual convention that I use is that I'm going to be using lambda squared for the eigenvalue and not for lambda. So that could cause confusion to people who are used to using lambda for the eigenvalue. But it saves me writing many square roots. So the square root of this eigenvalue is lambda j, and that's the frequency. 1 over the frequency is the wavelength. And we'll be discussing a lot about what occurs on one wavelength scale. So the frequencies are enumerated in increasing order, repeated by multiplicity. We heard about the Weyl law yesterday, and that counts the number of eigenvalues which are less than lambda. If M has a non-empty boundary, and that's going to be very important in this talk that M have a boundary for certain of the results, then we impose the standard Dirichlet or Neumann boundary conditions. So that's the notation. So when we have an eigenvalue, lambda squared, we denote the nodal set by n sub phi lambda. That's the zero set of the eigenfunction. And we denote the hypersurface measure by the n-1 dimensional Hausdorff measure. N is, for a generic metric, all the eigenfunctions are Morse, and the nodal set is a smooth hypersurface. But it's possible for the nodal set to have a singular set where both the function and the gradient vanishes. So I'll denote the singular set by sigma, and this is of codimension 2. So the nodal set is the zero set, and the nodal domain is a connected component of the manifold when we delete the nodal set. So the nodal domains partition the manifold into a finite union of disjoint open sets. And this is the way I write them down, omega j. And one of the problems we're going to be considering is to count the number of these nodal domains. When 0 is a singular value, the nodal set can have self-intersections. And OK, so n represents the number of nodal domains. So these are kind of classic, simple pictures in which the nodal set has self-intersections. So these are very non-generic pictures, but they're just historical pictures. This is on a square or rectangle, and these are the famous Chladni pictures of nodal domains. So we would be interested in counting, and as the eigenvalue goes up, at least apparently the number of nodal domains seems to go up. That's certainly true over here. As the eigenvalue goes up, apparently the number of nodal domains goes up. These are some very famous computer graphics of nodal sets, so it's good to stare at them for a while. On a Riemannian manifold phi lambda, if the eigenvalue is lambda squared, then lambda represents something like the degree. So these are the analogs of real algebraic varieties on a Riemannian manifold of degree lambda. And they look apparently quite uniformly distributed on the manifold, and it's very, very small, a lot of little small components of the nodal set. They look quite uniformly distributed on the manifold. Trying to prove any of those statements is beyond the state of the art at the moment. So here are the two problems that we're going to be considering. We would like to give upper and lower bounds for the Hausdorff measure of the nodal set, the surface measure of the nodal set in terms of the eigenvalue. And I just want to tie this together with the local global thing. Lower bounds are a local problem because if the nodal set has a very large hypersurface measure in any ball on the manifold, then it will have a lower bound, a large global lower bound. On the other hand, proving an upper bound is kind of a global problem because you have to be able to prove it everywhere on the manifold. Despite the fact that it's global, the techniques that people use are generally local techniques in which you break up the manifold into many small pieces and estimate the nodal set in each piece. OK, so then the second problem is to give upper and lower bounds for the number of nodal domains. And that's a fundamentally global problem. There's no way to recognize a nodal domain by just looking at a small ball on the surface. You cannot tell how it's going to be connected globally. There's a universal upper bound I'll mention later by Courant, which has been improved by Pleyel and more recently by Bourgain. But there do not exist any universal lower bounds. And actually, what we're mainly interested in this talk is the lower bounds. So I'll mention later on more detail, but Hans Levy constructed examples of spherical harmonics of arbitrarily large degree with only 2 or 3 nodal domains. So for general metrics and eigenfunctions, there's no lower bound that's valid for general metrics and eigenfunctions. Let me state a little bit more what I mean by local and global, just to hint at what different techniques are going to be used on these problems. When people talk about local methods, it means that they're studying, this is a local equation, you can study it on a small ball, and a small ball for us is going to be a wavelength ball. It's going to be some number epsilon over the frequency. A typical local analyst would rescale this small ball to a ball of size 1. So you might be rescaling sine of nx to sine of epsilon x. And on that length scale, the rescaled eigenfunction looks like kind of like a harmonic function, almost like a harmonic function. So it's very perverse to people in the global side of things, semi-classical analysis, to do this, because we like these rapid oscillations and we want to take advantage of them. So rescaling them to get rid of the rapid oscillation seems very perverse to us. On the other hand, we'll see that Logunov has been triumphant in estimating the volumes of the nodal sets. I should also say that this is a typical method used in many papers, but Logunov does not actually do this rescaling. Global methods mean that the eigenfunction must be an eigenfunction on the entire Riemannian manifold, not just on some ball. And that means that it's an eigenfunction not just of the Laplace operator, but it's also an eigenfunction of the wave operator. So the wave operator means that we take the Laplacian's a negative operator, so we take minus, and we take the square root to get an operator of order 1. And that means that the eigenvalues of the square root of minus Laplacian are the frequencies lambda j. And then we look at the unitary operator e to the it times that first order elliptic pseudodifferential operator. And to be a global eigenfunction means that it's an eigenfunction of the wave group, not just an eigenfunction of the Laplacian. And as that hints, almost all the global results take advantage of the wave equation to prove theorems. So one thing about the wave group is the Harmonic theorem on propagation of singularities, which is that singularities of waves propagate along geodesics. And by using the wave equation, we can relate the behavior of eigenfunctions to geodesics as the eigenvalue tends to infinity. That would be simply impossible in this local approach. And in the local approach, you just eliminate the high-frequency oscillations. So let me start and try to give you a survey of Logunov's proof. So this was Yao's conjecture back in, I think it was around 1978, if I'm not mistaken. So this is a very bold conjecture, by the way. We'll see in a moment. His conjecture was that for a compact C infinity Riemannian manifold of any dimension m, if you let the eigenvalue be minus lambda squared, then the surface measure should be bounded above and below by the frequency. There should be constants. I put these less than twiddles to mean there's a constant depending only on the metric. For some reason, I put the constant on the left and not on the right. But in any case, there should be constants depending only on the metric. And there should be a lower bound times a constant times the frequency and an upper bound of the same kind. Incidentally, it's not true that there's an asymptotic formula in general for this Hausdorff measure. If you did this on a round sphere, you'd find out that these constants can really vary with the eigenfunction. They're not constants in the space of spherical harmonics. This conjecture was proved in the case of real analytic Riemannian metrics by Donnelly and Pfefferman. This is a real masterpiece. If anybody is interested in studying this subject, this really remains a masterpiece with many unexplored and understood parts. However, it's much more likely that this conjecture is true for a real analytic metric than for a C infinity metric. Because, as I said, the eigenfunction is like a polynomial of degree lambda, and this is sort of like the Bézout bound. The upper bound would be like a Bézout bound, that the surface measure of a real algebraic variety of degree lambda should be roughly lambda. However, you also have a lower bound here, which tells you that the eigenfunctions have a lot of zeros. And that is truly special to eigenfunctions. There's no reason why a real algebraic polynomial should have zeros, much less a lot of zeros. So the lower bound is a bit more mysterious. The lower bound tells you that there are a lot of zeros. Maybe I could mention that I've recently given a global proof using Fourier integral operator theory of this upper bound in the real analytic case. And I won't take the time to explain how you do it, but it involves analytic continuation of the eigenfunction into what Gilliman calls a Grauer tube, and using the analysis of the analytically continued wave kernel to get all sorts of growth estimates. So the upper bound here, as I said, is kind of a global thing, and we have a global proof of it now in the analytic case. I haven't given up trying to give an analytic proof of this in the smooth case, but it's very unclear that one can do that. The lower bound, there does not exist a really good global proof of the lower bound. Alex Brudny has recently given a much improved proof of the lower bound over the original one in Donnelly Pfefferman. Okay, so that's the analytic case. For the C infinity case, it's really not at all obvious why you should have these kinds of bounds. C infinity functions don't really behave much like polynomials. So it was kind of a beautiful thing that Alexander Logunov proved the lower bound last year. And he did not prove the upper bound. I'll show you on the next slide what he did prove. And there is a prior history of these things. Bruning had proved the lower bound in dimension 2. Kolding, Menikotzi, and independently Sog and myself had proven a power law lower bound. And somewhat peculiarly, that same exact lower bound was reproved by 4 or 5 different teams. So it began to look as if the lower bound we proved might actually stick around for a while, but it did not. Logunov had just proved that his proof only works when the manifold has no boundary. That's surely true that his techniques should generalize to the boundary case, but so far, nobody has actually done that. So here's what he proved. He said, take a C-infinity Riemannian manifold. Then he proved the sharp lower bound of Yau, conjecture. And he proved that there is a polynomial upper bound. There's no real estimate on how large this alpha is. We'll see how that comes about later on. There's no estimate on it, so this is still a live problem. Hamid Azari proved that in negative curvature, or whatever alpha Logunov can give you, he can improve it just a tiny bit by a log lambda. So up until Logunov's proof, the upper bound that had survived since Hart and Simon's article in about the 85 or 87 or something was lambda to the power lambda. So this is a huge breakthrough here to get to a polynomial upper bound. All right. So how did he do this? Well, first of all, I'll explain what this means in the next slide, but he harmonifies eigenfunctions. That means he converts eigenfunctions into harmonic functions. Logunov is an expert on harmonic functions, especially on Rn. So, with the Euclidean metric. So this, I'll complain about this step later on, but in my write-up for this talk, I want to eliminate this step. So he harmonifies eigenfunctions and proves a theorem more generally for harmonic functions in terms of what's called the Almgren frequency function. And so his results are essentially about harmonic functions on a ball in Rn. It's extremely local. And the key objects that he uses are doubling indices. So when you have a harmonic function u, the doubling index is a function of a point on the manifold and a radius. So here P is in this ball. And the doubling estimate, we'll see the definition in a moment, but it sort of measures exponential growth rate in the ball of radius r. If I double the ball, to how much does the eigenfunction grow? Now, one of the reasons why you harmonify the problem is that this doubling constant is essentially it is a monotone function of r when you have a harmonic function. It is far from being a monotone function of r if you don't harmonify it. For eigenfunctions, it's not a monotone function of r. So what you have here is a family of monotone functions of r parametrized by points of a ball. And in some sense, that is all the data that Logunov uses in his proof. His proof is, to some extent, a proof about what happens if you have a family of monotone functions of R where it's a family parameterized by points of a ball. So he has to establish relations between these doubling indices as you vary the point of the ball. So this is such a minimalistic proof that nobody thought of it. So, well, let me go on. So let's see, what is harmonification? So harmonification just means that you take the manifold, you take the cone over the manifold. You take the manifold cross R plus. You use just the cone metric over the manifold, dr squared plus r squared times the metric on M. You let R denote the distance of the vertex. And then an eigenfunction can be converted into a harmonic function by taking R to the correct power. So the correct power is given by this formula. And it's a harmonic function in the sense that the Laplace operator on the cone kills the harmonic function. So this is almost equivalent to just taking e to the minus t times the frequency times the, this should be the eigenfunction here. This is just trivial that if you take e to the minus t frequency times an eigenfunction, then it will solve this equation. This is essentially the wave equation with imaginary time, which is the harmonic equation. And obviously, both this way of doing it and that way of doing it, which are essentially identical, just multiply the eigenfunction by a number, and consequently they have this very easily related nodal sets. All right, now here's the definition of the doubling index. The doubling index was, in some sense, a classical thing in quantitative unique continuation theory, but many people learned it from Donnelly and Pfefferman's paper. I'm positive there's an analog of this in the holomorphic world, but you take a ball centered at some point x, some radius r, and then you double the radius of the ball. And the doubling index of a harmonic function, or any function for that matter, is defined in this way. You take the ratio of the sup norm on the doubled ball and the sup norm on the original ball, and you want to see to what extent the sup norm grew exponentially as you doubled the radius, so you take the logarithm. So this is the doubling index, and of course there are many variations. You could take an L2 norm or some other norm here, and this is very closely related to Almgren frequency function, which I won't really mention. So Fanghua Lin, in his approach to nodal sets, likes to use the Almgren frequency function, but Logunov uses this one. The recent work also of Neighbor and Cheeger, which was also kind of related to getting Hausdorff measures of singular sets, uses the Almgren function, and I think this is actually a better choice. So a theorem in Donnelly and Pfefferman is that if you harmonify an eigenfunction with the eigenvalue lambda squared, then this doubling index is less than or equal to some constant depending on the radius times the frequency. So I want to pause for a moment here. When people use global methods, so this is like semi-classical analysis methods, and I noticed that Gilliman and Sternberg's new book on semi-classical analysis is up there. And what I mean by global is essentially the same as semi-classical analysis. We always have a Planck constant in the problem. And the Planck constant would be 1 over lambda. So somehow we have a Planck constant which is globally defined and sort of independent of the eigenfunction and of the operator. But key to Logunov's proof is the idea of having a locally defined Planck constant. And the Planck constant is local and depends on the choice of eigenfunction. You have a different Planck constant operating on different parts of the manifold according to how the eigenfunction grows. I have no idea how to implement this idea in any other problem, but I wonder if there is some way of doing it. So this Donnelly-Pfefferman thing said that the doubling exponent is bounded by the frequency. The constant depends on the radius in a very serious way. But it's very rare that the doubling exponent is anywhere near this amount. So so there are two things I want to mention here. One is that I've talked about the doubling index for the harmonic function, but you can also study it for the eigenfunction. And this is Fanghua Lin. Did this in several papers. But if you work it out, you find out that this doubling index is only monotone on a wavelength scale. So it's sort of like a Bessel function of the radius, actually. So it's a monotone function on a wavelength ball, constant over the frequency, but it oscillates a lot. So if one rescales, that's the Almgren frequency function, I should say, that oscillates a lot. But they're very similar. If one rescales the ball, however, rescales a small ball like this, then the eigenfunction becomes almost harmonic, and the doubling index becomes essentially monotone. So this is not a technique that Logunov used, but in my write-up for this talk, I'm going to try to reprove Logunov's theorem using this method. I dislike this method of harmonifying for the following reason. Namely, a big question, a quite open question, is try to figure out the points in the radii for which the Donnelly-Pfefferman doubling index is actually achieved. So that means that if you double the index, then you're supposed to grow exponentially where n is this doubling index. If you find a point in a radius where this actually is achieved, you've found what we call a ball of rapid growth, sort of a ball of exponential growth in some sense. Now, the simplest example of this kind where the doubling index is achieved is just to take r to the power lambda. Lambda is basically the same as n. This is the frequency, this is the doubling index in there. Well, if this is the eigenvalue, look at r to the lambda on 0 to t. On 0 to 1, it's 1. If you double the index, you get 2 to the lambda. So this kind of factor, r to the lambda, is a function which maximizes or extremizes the doubling index bound. This can be implemented on the Riemannian manifold. What's happening to this function is that it vanishes to maximum order at the origin. And that's the kind of ball where an eigenfunction is going to achieve the doubling index bound. It's going to achieve the doubling index bound if it achieves a maximal vanishing order at some point in the ball. So the maximal vanishing order, this is one of the nice theorems of semi-classical analysis, that the maximal order that the eigenfunction can vanish at any point is the frequency, the square root of the eigenvalue. And an example where it does that is the famous Gaussian beam. So if you want to study eigenfunctions, this is the first kind of eigenfunction to study. It is 0 to order n at the poles of the unit sphere. This is the 2-sphere. And it bulges out at the equator. So you can see it's going to vanish when x equals y equals 0. And this is the coordinate on R2, complex coordinate on R2. And I view this as coordinates on the 2-sphere, but the function is independent of the third coordinate. So that's a homogeneous polynomial of degree n, and we just restrict it to the surface of the sphere. Now, so this is the kind of example, and it's the only example we actually know how to construct explicitly. It's a very nice problem to try to figure out any kind of scenario where eigenfunctions actually achieve their maximal doubling exponent bounds. In fact, the points where they achieve it have to be very rare. Let me just go back to this for one moment. The harmonification is exactly, this should be the eigenfunction. So the harmonification is to multiply exactly by r to the frequency. So this is why I don't like the harmonification technique, because when you take the doubling index of r to the d times u, it's the sum of the doubling index of r to the d plus the doubling index of u. But you just multiplied it by something that almost extremizes the doubling index. So you're losing track of the doubling index of the eigenfunction because of this other factor. So I don't like this technique, and so I think it's worthwhile to try to reprove the theorem without harmonifying it. All right, now let's see why that should have anything to do with nodal sets. Here's another thing which is pure intuition. Nobody has actually ever proved this. Now, let's take the case where the eigenfunction vanishes to order n at a point. This could be like the Gaussian beam. It vanishes to order n at the center of the disk. If it vanishes to order n, or I call it lambda here, then you'll have n spokes coming out of the pole. See what I'm saying? It's going to look like, in polar coordinates, r to the n cosine n theta. And you're going to have n spokes coming out of the pole. Now, let's say that this is a ball, a small ball of radius 1 over lambda, but you have lambda spokes. So the length of this is a calculation we can all do even though it's pretty late. What's the length of the nodal line in this disk of radius 1 over lambda? We have lambda spokes. The radius is 1 over lambda. What do you think the nodal length is? Not a good sign. The radius is 1 over lambda. Each spoke has length 1 over lambda. We have lambda of them. What's the nodal length inside this disk? 1 maybe? Lambda times 1 over lambda. Okay, my point is there's a huge density of nodal set here in this disk. You see, we're looking at the points where the doubling index is maximal. And the only scenario we really know to produce it is maximal vanishing order. And we got to worry about those kinds of balls. because if we want to get an upper bound on the nodal set, these are really dangerous points because the nodal set is a huge length inside this, considering the radius of the disk. Everybody with me? The radius of the disk is 1 over lambda, and their lambda, okay, fine, good, okay. All right, so in a sense, in order to get an upper bound, you need to show there aren't very many points like this. Now, oddly enough, Logunov's paper never makes any relation between how large the nodal set is in a ball and what is the doubling index in that ball. Very strange. That's another missing intuition in the subject. Somehow one feels like the nodal set should only have a huge surface measure in a ball if there's like a huge doubling index in that ball. Donnelly Pfefferman have some results of this kind, but they don't come up in Logunov. So what does he do? So the first thing he does, and this is kind of a well-known intuition that has several different types of technical realizations in the field. The points with the maximal doubling index are very rare. So, in other words, cubes of rapid growth are very, very rare. So this is just a notation again. Logunov likes to call it n of x of r, and other people like to call it beta subharmonic function u of a point and a radius. And then you take, this is kind of called the uniform doubling index. You take the worst possible doubling index where you center a point in some cube Q. So this is called the uniform doubling index. So here's the theorem. Assume that we assume that the doubling index inside the big cube is less than or equal to n. And then we want to break up the big cube into a lot of little cubes. So I didn't know how to make a computer graphics of it, but I'm just saying that we have a big cube Q, like that, and we break it up into a lot of small cubes, which will be called like Qi. And the side length is 1 over a here, and we're in dimension n. So you have a to the n of these subcubes. They're little cubes. Now count the number of the small cubes where the doubling index is bigger than n over 2. So the doubling index on the whole ball is n. The uniform doubling index is n. So you've got to have point and a cube in there where the doubling index is n. So how often do you see that doubling index when you break it up into a to the n small cubes? And the answer is epsilon to a to the n minus 1. Now this is the volume of the set where you do that. If you sum up the volumes of the cubes where you get the doubling index n over 2, then it's less than this. So first of all, we see that the doubling cubes, the cubes of maximal doubling index, are kind of codimension 1 because the volume they fill out is a to the n minus 1. And the real result should be that they're codimension 2. Somehow points of maximal doubling index are like singular points, and singular points are codimension 2. So the points with maximal doubling index should roughly be called codimension 2, but it's a fuzzy notion. It's not really as clear, it's not as precise as singular points. So this epsilon in here, so this epsilon here shows you that it's a very small proportion of a at n minus 1. So just think intuitively that it's roughly codimension 2 in some sense. Now, if you go through Logunov's paper, this is kind of the main theorem in his paper. The main theorem in his paper is that the cubes of large doubling index are very rare. Notice that this is still a pretty large doubling index. He just took a half. Now, on the last page of his paper, essentially, is the first time that the nodal set gets mentioned at all. So there are no new theorems almost about nodal sets. Here's how nodal sets come in. He just defines a function of a real variable n, which is defined by taking a supremum of the Hausdorff dimension of the nodal set in a fixed cube Q. That's the big cube over here. Well, this could be for any cube. And divide out by the radius to the dimension minus 1, just to normalize the scale. Now, the point is what the sup is over. You take the sup over all harmonic functions on this ball and cubes, so that the frequency or the doubling index of the harmonic function in the cube is less than or equal to n. Bounding the frequency is like a compactness condition on the harmonic functions, like a growth condition on the harmonic functions. But this is the first and only appearance of the nodal set in his paper, is the definition of this function. So maybe it's good to stare at it for a little bit, because this is just a function of a variable n. And it's just that you're souping over a class of functions depending on n. Now, he wants to prove that this function has polynomial growth. If you can prove this function is polynomial growth, it means that the Hausdorff measure in a cube is polynomial growth in terms of n, and n is less than or equal to lambda, so you're going to get polynomial growth in lambda. Now, this might be a familiar condition or not. This is kind of a condition that a function has polynomial growth. In other words, if you say a number is bad, if f of n is bigger than some constant times n divided by n plus c, n over 1 plus c. So if you have a power of n, there are no bad points. This condition was used by Karamata in his proof of the Tauberian theorem, and it's called like functions of regular growth. So this, if you reverse the inequality, f is said to have regular growth. If you actually have this inequality, it's irregular. So you see that n to the alpha has regular growth. If you take n over n plus c, you'll get the same exponent n to the alpha on both sides. And, but if you take e to the n, every n is bad. It's never going to satisfy this inequality. So you want to prove, what Lagunov wants to do is prove that this function here is a regular growth, polynomial growth, outside, after n is some number. So for sufficiently large n, this is impossible. The reverse inequality is true. And when you prove the reverse inequality, it's basically proving that f has polynomial growth. So let me just pause for a moment there, because, you know, it's kind of strange. First of all, he's not directly studying anything to do with any specific function or what its nodal set looks like. He's souping over all the harmonic functions with doubling index less than or equal to n. That's a very original idea. It's sort of, you see this kind of idea in Nadirashvili's papers, but I've never seen it before being used here. And then you define this function f of n. And he cooks up this condition to show that the f of n is eventually a polynomial. Now, okay, now this is the most technical slide here, but this is the entire proof. I can put on Lagunov's entire proof on one slide. We want to prove that that function f of n is, there's no bad n. We want to prove there's no bad n when n is sufficiently large, and then f will be a polynomial. This sure doesn't tell you much about what the degree of the polynomial is. It's just going to prove it's a polynomial. So we're going to fix a bad n, and we're going to show that n cannot be too large. So let's see how large a bad n can be. And then you fix a harmonic function in a cube where this ratio, defining that function f, is bigger than 3/4 times f of n. So f of n was the soup over all this stuff, and we're going to find a u and a q which almost saturate the supremum here. Okay? So it almost saturates it, meaning it's bigger than 3/4 n. This is quite an arbitrary number. But you want the frequency of this harmonic function to be in less than or equal to n. You want it to be a competitor for the supremum in f of n. Now we're going to divide our cube q into a to the n equal subcubes. And then we'll divide the cubes into two groups, fast growth cubes and slow growth cubes. So remember that Lagunov's main and only result we've talked about so far is that there are very, very few cubes of fast growth. So fast growth is going to mean we fix some number c. These depend only on the dimension of the manifold. And fast growth means that the doubling index is almost equal to n. It's n over 1 plus c. And by assumption, it's less than or equal to n. And fast growth means it's bigger than n to the over 1 plus c. So we just divide the cubes into fast growth and slow growth. Now, this is the statement that we have a bad n. So we're going to use this statement over here. F of n is bigger than 4a times f at a lower value of n. And then what do we use about nodal sets? so far I haven't used a single thing about nodal sets except that f is a finite number. So let's try to see what we use. So we do the Hausdorff measure of the nodal set, and I use the fact that the nodal set, well, the Hausdorff measure can be broken up into the sum of the Hausdorff measures. It's a measure. So you can break it up into the sum of the Hausdorff measures where I sum over the different cubes in here. I look at the Hausdorff measure and I just break it up into the different cubes. So then I look at the Hausdorff measure in the good cubes, and I look at the Hausdorff measure in the bad cubes. And then I figure out how the Hausdorff measure relates to f of n. So in these good cubes, I get this kind of inequality. So the h to the n minus 1 over the diameter is always less than or equal to f of n. So I don't really get much of anything here. It's only in these fast growth cubes that I'm going to learn something. Because in the fast growth cubes, I have f at n over 1 plus c. And this is a different n than this one. But then in addition, I'm sorry, in the fast growth, I just garbled fast and slow growth cubes. But the point is that there aren't very many fast growth cubes. So we only get this big number for a very small number of the cubes. And over here, I'm going to replace f of n over 1 plus c by the definition of f of n over here. And that 1/4 here is the same as the 4. Is the same as the 4 in the definition over here. So yeah, here I have it over here. You get this 1 over 4a coming in. So when you have this f, you can use this inequality over here, and you end up with, by the definition of f, you end up writing this down. And when f is f of n, you get this one. And so you add them up, and you get 3/4. You get that this is less than or equal to 3/4 f of n. But by definition, n was bad, so it's supposed to be bigger than 3/4. That's a contradiction. So the contradiction came from assuming that this cube was bad over here. We just assumed it was bad. That allowed us, we broke it up into the sum over good cubes and bad cubes, and just replace hn minus 1 by, I just multiplied it out. Hn minus 1 is equal to f of n times the diameter. That's all I did. And we just, that the n changes in the good cubes and the bad cubes. There's a different n in the good cubes and the bad cubes. That's the whole thing. That's the whole argument. And we use in the first one here that there aren't very many of these bad cubes where we get this big f of n. In the second one, we have a relatively small f at n plus 1 over c. So anyway, this is not easy to absorb in 5 minutes or less, but it's the whole argument in this paper. Yes?
Everything is uniform and independent of the manifold.
No manifold, no nothing. We didn't learn a single thing. Did anybody learn anything about nodal sets just now? We did. We learned we have polynomial growth of the polynomial growth of the nodal bounds, but we never learned any new relations between growth of the nodal set, growth of the function. All we ever used in this argument was this one fact that there are very few cubes of fast growth. This over here is sort of means fast growth, is very bad n. And we just measured the nodal set in the cube Q, which is just like the unit ball or the unit cube. There's nothing about it. And we're souping over U. So this is the U, which should have the largest nodal set. So we just use the fact there are very, very few cubes which have a large doubling index. We never related the doubling index to the nodal set, ever, except by the definition of F. It's a very strange argument. I am not joking. This is the whole argument. What did you ever use about nodal sets? Well, the nodal set in the big box is a union of the little pieces in the small boxes. That's basically all you're using. That's basically all you're using. I mean, this same proof could prove a lot more than just polynomial upper bounds on nodal sets. If you can figure out another quantity to measure for which you have these monotone families of functions and for which you can measure the thing in a big box by breaking it up into small boxes. It's a very, very interesting argument and sort of surprising to everybody because all we're ever using is the existence of these family of doubling constants. And using the family of doubling constants is what proves this result. It also doesn't really have much of anything. It just uses doubling constants and their monotonicity. And then here, first time we ever introduced nodal sets into the problem. And it's through this function f of n, like this. First time the nodal set and its hypersurface measure comes in. And what are you ever using about it? You want to prove it's polynomial. So by contradiction, you say, well, suppose it grows like that. It's like exponential. And then you get some contradiction from the fact that there aren't very many cubes where the growth rate is actually equal to n. On most of them, it's actually n over 1 plus c. Very, very strange argument. I tell you that, we could spend the rest of the hour just staring at it, but you could also spend the rest of the month just staring at it because it's quite a subtle argument. And I don't know, I guess I wanted to contrast this to another problem. I didn't want to let the local analysis people triumph too much, so I want to give them a theorem where there's no way that they can possibly prove the theorem. You need four integral operators in microlocal analysis to prove this theorem, so just as an advertisement for microlocal analysis, I want to give a theorem you can't prove any other way. That's the famous last words. So, namely, how about counting nodal domains? So this is actually a conjecture in Yao's most recent problem list. So the thing is that the hypersurface measure of a nodal set, you can measure it by breaking it up into lots of pieces, measuring it, and adding it up. But nodal domains, you cannot do that. You cannot tell if something's a nodal domain or not on a local scale. The connectivity of it is a global property. So here's a good question. And if there are any graduate students who want an interesting problem in classical analysis, this is actually, although I put it this way, it's on Yao's problem list, so it counts now as one of Yao's problems. But namely, well, let me just state this before stating the problem. So how many connected components does a nodal set have? How many nodal domains are there? It's essentially the same question, at least on its surface. So the Courant proved in the turn of the century, 1920, that the jth eigenfunction in order of the eigenvalue has no more than j plus 1 nodal domains. So that's a universal upper bound. Far from sharp. Pleyel improved it, Bourgain improved it, but the rather fantastic paper of Nazarov and Soden proved that a generic eigenfunction or a linear combination of eigenfunctions achieves this in order of magnitude. I don't have time to explain what I mean by that, but this bound is pretty sharp in a certain sense. Not in terms of the constant in front of j, just order of magnitude. However, there's no non-trivial lower bound. So this was actually a theorem of Hans Levy that, in fact, on a sphere, many people have done this now, but on a sphere, there are sequences of eigenfunctions with only 2 or 3 nodal domains. So here's the problem. I can't believe this is a hard problem, but I can't prove it either. So good challenge for somebody in the audience. Give it to your undergraduate class and see what happens. So let's take just any compact Riemannian manifold, okay? Or maybe a generic one if you need to. Show it has some sequence of eigenfunctions for which the number of nodal domains tends to infinity. Levy had to work really hard to get these sequences where you have only 2 or 3 nodal domains. Is it possible there's a Riemannian manifold where every eigenfunction has no more than 10 nodal domains? So Anyway, that's the problem. And, okay. In fact, how many manifolds do you know for which Riemannian manifolds you can prove that the number of nodal domains tends to infinity? I can enumerate them for you. A flat torus, a round sphere, and nothing else. So, all right. Now let's take a look at what this is. So, you look at them and you see it has a lot of nodal domains. These are really generic things. They have a lot of nodal domains. It's ridiculous that you can't prove that they have that you can't prove that the number is bounded or it goes to infinity. So, at the moment, the only mechanism that we can use to prove it is ergodicity of the geodesic flow. So that is a very global condition on the Riemannian manifold. So this is a very vague intuitive idea that if billiard trajectories are ergodic, that means they're all uniformly distributed, then the nodal line should wander uniformly around on the manifold, and there should be a lot of nodal domains. It's just very, ergodic on the classical level implies extremely oscillation on the quantum level. That's basically what ergodic means. Things are oscillating a lot. And if they oscillate a lot, they should have a lot of zeros everywhere. So that intuition is not going to get you anywhere, but it's the intuition. So here's the first theorem. So this was proved by Junhyung Chung and myself in a variety of different contexts, but this is my favorite of the results at the moment. So we look at a surface of non-positive curvature and concave boundary. Okay? So this is what's called the Sinai billiard, Sinai-Lorentz billiard. So it's highly chaotic. Then for any orthonormal basis of either Dirichlet or eigenfunctions, you can find a density 1 subsequence so that the number of nodal domains tends to infinity. So density 1 means what you would think it means if you thought about it. So almost all the eigenfunctions, almost the entire sequence of eigenfunctions, the number of nodal domains goes to infinity. Okay? So that's the theorem. Nobody knows about the potential sparse subsequence where it does not happen. So this is a picture of what a Sinai billiard looks like. This is like taking out a disk out of a square. So this is a Sinai-Lorentz billiard, and when you take out the disk, the billiard ball bounces very dispersively off the boundary, and so this is a highly chaotic billiard table. And you need to use the chaotic behavior in order to prove that you have a lot of nodal domains. So how does that go? Well, a more recent paper actually gives a lower bound. And I think you're not going to be able to improve this in a while. So if this is in the boundaryless case, but it sort of imitates the boundary case in the boundaryless case. I'll show you on the next slide. It's called the real Riemann surface, and you take a negatively curved invariant metric. And then, again, for a subsequence of density 1, you actually get a rate at which the number of nodal domains grows. So this may not look like a very impressive rate, but it shows that you're growing at least like a power of the logarithm along a density 1 subsequence of eigenvalues. So we didn't know, the previous theorem just said the number goes to infinity, but gives you no rate at which it did. These logarithms are a ubiquitous feature of spectral theory when you're dealing with flows that grow at exponential rates. You hardly ever can get rid of them. Selberg introduced this logarithm into the Weil law in 1955, and that has not changed to date. So this is a real Riemann surface. It's a surface with an anti-holomorphic involution, which means like complex conjugation, top to bottom. And the fixed point set of the involution is a real algebraic curve. So this thing is the complexification of a real algebraic curve. Now the point is that the fixed point set of this involution is exactly like the boundary of a surface with a boundary. I just cut the thing into 2 pieces along the boundary. It just so happens that our knowledge of boundary problems is not good enough at present to get this lower bound. Even to get this lower bound, we had to use Melrose's theorem on Weil law for manifold to concave boundary and actually improve on it in certain respects, just to be able to prove this. So let me just give a hint as to how this goes. I have no idea when we started. I have no idea when we're supposed to end, but I figure if you're hungry enough to, well, never mind. So, how do we prove it? And this is kind of strange. So, before I get into this, the way that we tend to prove almost everything about nodal sets with global methods has to do with restricting eigenfunctions to curves and counting the number of zeros on curves. Now that sounds like incredibly primitive math. But if you think about it, it's not really that primitive because the Crofton formula tells you that if you want to measure a hypersurface volume, you just measure the average number of zeros along a random curve, like a random geodesic arc. So by the Crofton formula, if you really do know the number of zeros an eigenfunction has on a curve, you will know its hypersurface volume. Okay? So the thing is, however, that there's only one curve which gives results about numbers of nodal domains. And that's like a topological problem. You need the curve to be the boundary of the manifold. Or in this case over here, it has to be the fixed point set of the involution, which is essentially the boundary between the top and bottom. This is because of the topological reason why. But what you can prove is the number of nodal domains is greater than or equal to 1/2 the number of zeros on the boundary. I can give you a really simple picture that sort of explains why it's true. So suppose you have a surface with a concave boundary, and you have some topology. You have a bunch of zeros of the eigenfunction on the boundary. Well, if you're lucky, it just goes out like that and comes back, and you have a nodal domain. But if you're unlucky, this thing might loop around and come back, and you don't trap a nodal domain. But this problem here about the thing coming back without forming a nodal domain, it has to do with just the topology of the surface, and there's a fixed genus, and we're letting lambda go to infinity. So if we can prove that there are more and more and more and more zeros here, you're going to get more and more things that do that, and you're going to bound the region in between. Another thing that could happen is that you have another nodal component here, and the nodal line could hit that component and stop. But actually, that turns out to mean more nodal domains, not less. So it's not a problem. So this insight that you can get numbers of nodal domains out of studying zeros on curves was lifted from a paper of Gosh, Reznikov, and Sarnak, who studied what's called the modular domain. But we had to use a somewhat different argument because their argument didn't really apply. But it's sort of, that's the insight that sort of started this off. So now we're reduced to showing that these Neumann, like let's say Neumann eigenfunctions, have a lot of zeros on the boundary. Or if you're dealing with Dirichlet, you have to have a lot of zeros of the normal derivative. And that is like a classic problem you can find in Polya and Zago, but it's a really interesting classical problem. How do you prove that a sequence of functions has a lot of zeros on the circle? Suppose you just have a sequence, Fn, of functions on a circle, and you want to prove that the number of zeros is growing. What are the conditions? What kind of conditions? You want the functions to oscillate a lot, but they can oscillate a lot without ever being zero. So the trick to proving that these functions have a lot of zeros on the boundary is to show that for every small arc on the boundary, beta, the integral of the function is much less than the integral of its absolute value. Okay? And of course, this means that it has to have a zero. Otherwise, these two integrals would be the same. So we need to be able to prove this estimate. If you want to get a rate at which a number of nodal domains grows, then you have to prove this for an interval which shrinks. So to get the logarithmic rate, we had to let it shrink like 1 over log lambda, and then on every interval of radius 1 over log lambda, you have a 0, and therefore you're going to have log lambda zeros. So I just want to maybe end with one slide. Like, where did the four integral operators come into the problem? And this is a series of results that have been studied by myself and with Hassel and with Toth and Hans Christiansen, which we call quantum ergodic restriction theorem. So this is a new kind of quantum ergodic theorem. And it's an exact parallel of a theorem in dynamics that says that if you have a flow, which is ergodic, and you have a cross-section to a flow, then the first return map is ergodic. So we're really just doing a quantum analog of that. And it comes down to this statement. So this is just a special case of it. It's a very general theorem. But we take an arc on the boundary. Then for a subsequence of eigenfunctions of density 1, the integral of f against phi j squared goes to the integral of f. Or you can just say that on that arc, phi j squared over the arc is basically tending to 1. So the point of this is that eigenfunctions restricted to the boundary, Neumann restricted to the boundary, cannot be small. If you integrate their squares over any arc, it has to tend to like the length of the arc. So this is, that's sort of the way it works. And I'll just say this really quickly. I think I've run out of time. But it's putting together the following bunch of inequalities. If you integrate this eigenfunction over a short arc or against the continuous function, it has a pretty big decay rate. This is what I call a Kuznetsov formula, and it's a kind of Weil-type law. It follows from a kind of Weil-type law. So it's one use of the microlocal methods and the wave equation methods. I don't know any other way you're going to prove it. The second thing is that, well, this says that the integral of f against the eigenfunction is really small, but maybe it's because the eigenfunction is really small. And the second, the quantum ergodic statement is that the eigenfunction is not small. If you integrate the eigenfunction against any continuous function or characteristic function of any arc, it's going to be greater or equal to 1. So this thing is small because this function is oscillating a lot, not because the function is small. And then we have to use a sup norm bound. And this is what's hard on manifolds with boundary. This is a standard result on a negatively curved surface, and there's no sort of analog at the moment on a non-positively curved surface with a concave boundary. But anyway, we just put these results together by using the simplest possible thing. Namely, the integral of the L2 norm is bigger than 1, but this is less than the sup norm of phi times the L1 norm of phi. And then we use the bound on the sup norm. We sort of put it together. And we find that the integral of the absolute value has this bound, but the integral of the non-absolute value has a slightly smaller bound by just like a little smidgen of a logarithm here. So we're really, we don't have much room for maneuver here. And that's how we prove that there have to be a 0 in every small arc on the boundary. And then we look at this picture, and that gives you a topological argument there have to be a lot of nodal domains. So that's where I'll stop.